For nearly a century, our cosmic origin story has been one of unimaginable fire. A universe born in a singular, violent and incandescent moment, the Big Bang. We've been taught that the faint afterglow of this creation, the cosmic microwave background or CMB, is the cooling ember of that primordial fireball. It's a beautiful story supported by decades of evidence. But what if the story is incomplete? What if the universe wasn't born in a flash of heat but emerged from an infinite, profound cold? This is the starting point for a radical new idea, the cold CMB hypothesis. It asks us to set aside the inferno and imagine a cosmos born from absolute stillness. This new perspective doesn't just tweak the details, it rewrites the opening chapter of our universe. Instead of an explosion pushing everything outward, imagine a perfectly motionless, ultra-cold vacuum, a state of pure potential. In this model, the motion we see everywhere, spinning galaxies expanding space, isn't the leftover momentum from a blast. Instead, it's a property that emerges from the vacuum itself. The universe in this telling didn't begin with a bang. It began with a deep, silent hum that slowly grew into the grand cosmic symphony we witness today. It's a profound shift in thinking, moving from a chaotic origin to one of emergent order. Our current champion of cosmic origins is the Big Bang model. It's a powerful and successful theory. It tells us that about 13.8 billion years ago, all matter-energy space-time was compressed into an infinitely hot, dense point. This singularity exploded. As the universe expanded and cooled, fundamental particles formed. Atoms formed, stars formed, galaxies formed. The cosmic microwave background is presented as the definitive proof, the leftover light from a time when the universe was a scorching, opaque plasma, now cooled to a mere 2.7 Kelvin. It's the echo of that first fiery moment. But every great theory has its puzzles. The standard model requires a period of hyperfast expansion called inflation to smooth out the early universe, a concept we don't fully understand. It also posits a hot beginning for the formation of light elements like helium-lithium, a process called Big Bang nucleosynthesis. The cold CMB hypothesis offers a different path. How can motion and matter arise from a cold, empty void? The answer may lie in a concept called vacuum field instability. Imagine the vacuum not as emptiness but as a field filling all of space, like a calm sea. The cold CMB hypothesis proposes that this initial superstill state was false vacuum. Over immense stretches of time, this field can spontaneously decay, transitioning to a lower energy true vacuum. This transition isn't violent or instantaneous. It's a gradual process across the cosmos, releasing a tiny amount of energy. This released energy doesn't just disappear, it condenses, like cold air causing water vapor to form fog droplets, forming ultra-cold, low-energy condensates. These aren't particles as we typically think of them, not protons, not electrons. They are something new, something more fundamental. These condensates are the very first structures in the universe, emerging from the featureless void, the first step away from perfect symmetry and stillness, the seeds from which future complexity, including matter, will grow. They are the universe taking its first breath. A scientific theory is only as good as its predictions. The cold CMB model makes a very specific one. The universe should have a background radio hum strongest around 1.6 gigahertz. That isn't from stars or galaxies. So have we seen anything like it? The answer is a tantalizing maybe. In 2011, a NASA balloon-borne instrument called Arcade-2 measured the radio background of the universe. When its scientists subtracted all known sources, our galaxy's radio glowed distant galaxies everything they could account for, they were left with a surprise. There was a leftover signal, a radio hiss 6 times louder than anyone expected. This space roar, as it was nicknamed, remains one of the great unsolved mysteries in astrophysics. No known population of stars or galaxies can explain it. The standard Big Bang model doesn't predict it, but its properties are intriguingly similar to what the cold CMB hypothesis suggests. While the Arcade-2 signal is a broad spectrum, its existence proves that there are powerful, unexplained radio sources out there in the cosmos. Could this be the signature of oscillating condensates, the hum of a universe waking from a cold slumber? The standard Big Bang model tells a compelling story about where the elements came from. In the first few minutes after the explosion, the universe was a hot, dense soup of particles, a perfect furnace for forging the lightest elements. This process, called Big Bang nucleosynthesis, predicts 75% hydrogen, 25% helium trace amounts of lithium. This prediction matches our observations of the oldest stars and gas clouds, and it's considered one of the great triumphs of the Big Bang theory. But the cold CMB hypothesis requires us to find a new home for all that helium. If the universe started cold, there was no primordial furnace. So where did the helium come from? The theory proposes a startling answer. It was made later inside the very first stars. We call this idea Grok nucleosynthesis. The first generations of stars were far more massive and efficient at creating helium. They burned through their hydrogen fuel rapidly, converted huge portions into helium, and seeded the cosmos long before galaxies formed. This leads to a provocative idea. For so long, our scientific and philosophical picture of creation has been tied to chaos. A violent explosion, a universe forged in fire, a cosmos born from a rupture in nothingness. The Big Bang model gives us a universe whose fundamental properties were set in a moment of unimaginable violence. The expansion of space, the distribution of matter, the very motion of the galaxies, all are seen as the fading echoes of that initial chaotic event. It's a powerful and dramatic narrative, one that resonates with our own stories of conflict and resolution. The cold CMB hypothesis offers a profoundly different vision. It paints a picture of a universe born not from chaos, but from stillness. It begins with a state of perfect, cold, silent equilibrium. Order doesn't emerge from the ashes of an explosion, it is awakened from a state of deep potential. Motion is not a remnant of a primordial push, but a property the universe generates for itself, a cosmic self-awakening. This is a story of becoming, not of recovering. It suggests that the fundamental nature of reality is not chaotic but deeply, profoundly ordered.